Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce today Dan Povey, who is here for a couple days from IBM Research. It was my privilege for several years to work with Dan. He's one of the most creative and diligent at the same time,
diligent, really. I'm surprised you chose that adjective.
and successful researchers that I know of. And so although he does engage in false advertising, I'm sure his talk today is gonna be very interesting. So thanks, Dan.
Thanks. Okay, so as you know, I was originally billed to talk about discriminative training, but I really don't think that there's too many people here who would be interested in that. And if there are, then I could probably much more usefully speak with them privately. So I really wasn't sure what to talk about, and I thought it would be interesting to just talk generally about what I think is interesting right now, because this is the kind of thing that we speak about when we're informally chatting with each other, and I don't see the harm in moving that over to a more formal setting. So I asked people at IBM, so I wasn't talking about what I personally thought was interesting. I asked everyone, what do they think is the most interesting areas now? And in some cases, I got useful answers. In some cases, people didn't really name anything. So just an overview of the slides. I'm going to briefly tell you in one slide what my own work was about, so that you know where I'm coming from and what my biases may be. And then I'm going to talk in various categories. SVMs, in the past few years, a lot of people have been speaking about that. Not necessarily endorsing them. With SVMs, I have my reservations, but I'm going to talk about other discriminative training work. I'm going to talk about, as a general category, ML acoustic modeling work, various front-end tinkering that people are doing, this whole neural net for front-end trend, this Bayesian networks and belief propagation. I wasn't going to have that originally, but someone mentioned it as their favorite category, so I put it in. Language modeling, noise-related feature work, which I personally think is quite interesting right now. Yoshi isn't here, right? He was discouraging me, saying, "What? Why don't I see him? Is there something wrong with my visual system?" Oh, I'm sorry. So you're right over there. Sometimes you see something and you just don't register. Other acoustic adaptation, LM adaptation, and the miscellaneous stuff, which no one is really working on. Okay, just to briefly introduce you to my own work, you may or may not know. Originally, I was working on some implementation issues in MMI. I was working for that, and the next thing I was working with Phil Woodland. Basically, my contributions to MMI were just to refine the lattice-based training setup, introduce a new way of doing the updates with the extended bound-Welch equations, and just investigated various issues about likelihood scaling and language models. After working with that for a while, I came up with an alternative discriminative training criterion called MPE, which is more closely related to word error rate than MMI is. And in that sense, it's you can look at it in a way that it's similar to MCE because it kind of has a sigmoid in it, but it's not kind of at the whole sentence level. It's at the phone level, which I feel is more appropriate. At IBM, I came up with something called fMPE, which is like a feature-space version of MPE, where you use the discriminative objective function to train this. It's like a front-end projection, very large dimensional projection of your features. So you can have as many parameters as there are in your acoustic model, and it improves the error rate, so you get worthwhile improvements. It's the transform is similar to that used in Splice. Yeah, generally speaking, a lot of the work in this thing, it involves practical issues like learning formulae, learning rate, stuff like that. Yeah. So it seems like in the last few years, a lot of people have been pushing SVM approaches into speech. And at least a couple of my colleagues at IBM mentioned this SVM stuff as their favorite work. And I'm sure there are some people in the audience who are big proponents of SVMs, and I really don't want to upset them, but you'll have a chance to respond to my objections. Now, I find SVM stuff extremely annoying because they talk for so long about this theory that there are these bounds, these Vapnik, whatever bounds, whatever they call them, and about how they limit your test set error. But if you actually look at these bounds, they're useless bounds. You know that they're nowhere close to anything relevant. Now, SVMs are defined for two-class problems, which make them very hard to apply to speech. And I think when people modify them for speech, it takes away most of the SVM-like aspects of SVMs. Like you get rid of the support vectors, so it's really no longer SVMs at all. So none of this theory applies. And often the things that you end up with look just like an original technique that existed in some other form. I have another general objection which isn't listed here, that often it seems like SVMs is just some kind of nearest neighbor technique. And there's a lot of theory which may help you slightly in updating stuff, but it seems like it's not a vast change in, it's not a vast contribution. Perhaps the thing that people were talking about when they said SVMs are most interesting is this SVMs for discriminative training, which a few people have been working on. And they seem to be getting good improvements. But I just wonder how well this will scale up, because basically it seems to come down to something similar to MCE, where you have like n different hypotheses at the sentence level, and one of them is correct, and you try to make that one the most likely. Then you have various different soft margins and stuff, which you try to optimize stuff. But if your sentences are extremely long, if you can't segment your data, then there's only going to be one or two places in the sentence where things are actually going to be confusable because of the way n-best lists are generated. And there's no real practical way that you can have a million n-best or something to get the rest of the sentence. And then if you decide to break it up, it's very hard, because if you break it at each word, the context is very important. So I really don't see how these problems can be got around. And my feeling is that theoretically MPE is a better way to handle these issues. I mean, okay, that's the end of the SVM slide. So I wonder if there's any SVM believers here who feel as if they need to respond to these objections.
Well, I mean, number two, actually, because we saw one. It's multiple class. The books chapter talking about that. Actually, in the last week, LIPS, people even develop semi-supervised SVM methodology very interesting, because.
Okay, I guess I haven't been following SVM research as closely as I should.
I'm not a proponent for that, but I thought that there are some complementary properties.
Yeah.
For instance, convex optimization, I think these are very important. With that, probably avoid a lot of optimal the traditional distribution.
Yes, I suppose from an optimization point of view, maybe there's something there.
Well, it's a different way of doing the same thing, I think. You were talking about how it's important to, for example, not optimize the hell out of your objective function, but do it smoothly.
Yeah.
What the SVM folks essentially do is they make a convex approximation to the objective function very close to where you are in the ML solution, and then just throw a fast optimizer at it. And essentially it's a different way to be careful.
Okay.
That's what it boils down to, right? It's do MCE with a different way of being careful is what, in practice, it'll boil down to.
Yeah.
So who at the end
Well, George is a believer in SVM. We'll have arguments about this because he gets upset when when me and some other people disparage SVM. And then I think Brian Kingsbury was not in this context, but he was mentioning one of these papers as. Yeah.
I mean, if you really can find a large margin and maximize it. I mean, it seems like a pretty reasonable thing to do, right? I mean,
well, in a limited, for isolated digits, I can see your point, and I would agree with that. But the thing is, for a sentence, I think it's a big problem.
I mean, we're in this really high, in fact, infinite dimensional space. And so what does it mean to have a large margin in this infinite dimensional space? Because everything's very far away from, it's a very sparse space, right, that your sentence just said it.
no, I mean, you know, you could still, you still could have a very high margin, right? In other words, you'd say that basically that the true string, you somehow found this classifier such that the true string is a long
So if
way
you could
away
find
from
the
all
right
the others,
kernel,
right?
yeah.
No, exactly. So I mean,
But wait,
so it seems
in
to
a
me-
very long sentence, the correct sentence is never going to be the most likely. There's always going to be some error in it.
Well, so what I was going to get at is that once you start to introduce these slack variables, which you need to have in the case when the problems aren't properly separable and stuff like that, then I think all these advantages start to go away, and then this just becomes, you know, I mean,
This becomes the same as any other discriminative
another-
training.
Yeah, exactly.
Experience on that directly.
Yeah, yeah.
Sometimes more challenging to deal with.
I mean, maybe I don't object to the techniques in themselves, but I think people are claiming that it's some whole new paradigm, where really it's just a slightly different method of discriminative training. Anyway, just wanted to mention various other discriminative training approaches. None of these are earth-shattering, but I just wanted, as it's a general review, various people have, proposed various things that look like MMI or MPE, and I tried a few of these recently. I have an upcoming paper in ICASP, but Jing Zheng at SRI, he has something called MPFE, which is an acronym which is surprisingly hard to remember. But it's like a frame-weighted version of MPE, and it appears to be better. Previously, I tried it, and it turned out there was a bug in my code, so I wrongly believed that it didn't work. It does seem to work, although the improvements are relatively small, especially if you're doing
Are you talking
fMPE.
about the stuff you did with Woodland, the frame-based stuff? Or
You did that with Phil?
no, how long ago did you do the frame-based stuff that you had a bug in?
Oh, no, that was at IBM, because Jing Zheng, he published that only a couple of years ago.
Okay.
But it's only now that I found that it really works. There are various other people who have various modified approaches that I tried to, but I couldn't replicate those.
My problem with the frame-based MPE is that for a single frame, I mean, there's no ground truth to it, right? If you just listen to one, you don't even know which phone it belongs to.
I see what you mean, but in practice,
viewers,
MPE has the same problem because
But it's less-
no,
it's less problem.
Well, the way I measure the objective function, I don't do like a string alignment. I actually use the frame. It's based on frame overlap. It's an approximation. So really, the same problem. It's just a different weighting. I mean.
Sorry, I didn't want to interrupt in here, but could I ask a high-level question?
Yeah.
So my area is computational linguistics, and
Yeah.
we've also been doing a lot of, max marginal decoding instead of searching for the Viterbi, the global most likely analysis. In fact, because max marginal decoding corresponds better to our evaluation metrics, in other words, because we tend to score, say, the quality of parsers on a node-by-node basis, in fact, actually, you can get higher scores by coming up with a parsing process that in fact actually assembles the parse tree so that it's not the most likely parse tree, which is a global thing, kind of like, doing Viterbi analysis from an HMM. But instead, you wind up, sort of asking for each node, okay, pick the most likely node that spans this particular substring.
I'm not sure that I understand how that works,
Yeah.
but I guess it's because I know.
That's right.
with the
So
general
then there
framework.
still is a dynamic programming algorithm for finding the tree that contains the sum of the most, where the
I mean, is
scoring
there a well-defined objective function, or is it just procedural?
There is a well-defined objective function. It's a different objective function. So, but anyway, the high-level question is roughly as follows. At least inside of computational linguistics, I think there's the sense that even though we're scoring better, we're actually not producing better parsers. Right? In other words, if you look at the tree, it's not a better tree. It's just a tree that happens to score better on our evaluation metric. And I wonder whether the same thing's happening here too. In other words, are
You mean that
really
I may not
actually-
have the correct objective function and we're optimized?
Yeah, I mean, so basically you've got some objective function it doesn't necessarily correspond to
Yeah.
producing better speech recognition output, right? Which I presume is what you're going after here.
I'm sure that's true in general, but I think it's hard to come up with something that's going to capture really what you want. It has to be computable and easy to define.
But I mean, is there a danger that you're just optimizing your objective function? You're not, and the objective function itself.
I don't know. My feeling is that the objective function is pretty good, and the more of a problem is overtraining. That's my feeling, but it's hard to be sure. Yeah.
So I kind of want to the question. According to this kind of argument, if you use WPE, word-based discrimination, ideally you should be doing a lot better. But for
Because it's more closely related. Yeah, it's slightly worse. I mean, I think that the reason is.
What's your intuition?
I think it's just to do. I think it's to do with generalization. That if you had infinite training data, MWE ought to be better. But I tried to.
If you cheat on the training set.
Oh, I think actually what you say is true. I think actually you do get better on the training set. I tried to verify this a different way with just very small models and large amount of training data, but I couldn't really find any advantage. Anyway, I mean, yeah. So a couple of other things I wanted to mention. Just because there's some work in this area, I don't necessarily think it's improving things, but BBN has a different thing similar to fMPE where they look at it as a region-dependent transform, and it has certain generalities which are allegedly good. Mark Gales also has a model-based interpretation of fMPE, and that, again, doesn't seem to have led to word error rate improvements. I mean, maybe it can be extended in different ways, but I guess we have to wait. The discriminative version of splice, I'm not sure that I've fully understood that. I'm sorry, Asha, but is it correct that it's limited to some kind of adaptation situation where you have stereo data?
No.
No. Oh.
It's
FMPE.
squarely in the same place as all these other algorithms you're talking about. It's like fMPE, only not as powerful, because we don't have the extra context for the frames and things of that nature.
Yeah.
It's a very small number of parameters.
Yeah. I mean, it seems to me generally that these techniques, they ought to be good at, they ought to be extensible, because you ought to be able to introduce lots of fancy other nonlinear things in the front end. But I think in practice, I haven't been able to do it myself yet, and I haven't really put enough time into it. Again, this is not necessarily the most exciting area. I just wanted to mention some stuff which I thought was interesting. Are you familiar with the IBM work that they had on spam and those various front-end techniques? Peter tells me that out of all those various covariance modeling approaches, spam is really the one that you ought to choose if you had to choose. And I actually worked with spam myself a little bit, and it's very good if you have limited Gaussians. You get quite big improvements relative to normal diagonal Gaussians. But if you have as many features as you want, the best result you can get is just with a smooth full covariance system.
Just for the non-speech person like myself, can you explain what a non-front-end acoustic model would be?
I'm talking about I see what you mean. Well, I guess I'm talking about stuff that doesn't involve changes to the front end, stuff that's not like splice or fMPE. So, I mean, some techniques involve some messing around at the front end with the features, whereas the back end is like the model itself.
So it's
just model domain.
So these change the features as they come in. Other techniques you just change the acoustic model that you're using to then decode those features.
Oh, I see.
John McDonough has recently had some papers where he says that it's important to do SAT, by which he means it's this thing with with MLLR as opposed to fMLLR. And it's a slightly more complicated method of speaker adapted training than just rotating your features with the fMLLR transform and training. You have this whole, this whole linear equation to solve. And he claims quite large improvements, though personally I've I tried SAT just for the regular ML case, and I didn't get any improvements at all. I don't know if it's because I was trying on an existing trained system, but it seems to be something that might be worthwhile trying because it's easy to do. And the next.
Well, not if you do it John's way, right? Because the way John does SAT, he insists on doing the simultaneous optimization, which means you need to reproduce all the counts for each speaker separately.
Simultaneous optimization of the speaker transforms.
Of the speaker transforms and the models.
Oh.
And so there's this blow up of space.
I guess I wasn't aware of that.
And
so like within each maximization operation, you do this simultaneous. Oh. So maybe that's why he's actually getting improvements.
But, I mean, it's not easy to do.
I see.
It's still not, he gets bigger gains, but it's still not clear.
I see. Maybe I didn't read his papers carefully enough. And he also claims that there's an MMI version of SAT, which is really good. And I never really understood that either, I'm afraid. A rather small category. There's various people who are proposing front ends which are kind of equivalent to MFCC or PLP, in which they claim is better. And someone with a good system who we can really believe is going to have to check that that's true. There's this whole category which seems to be building momentum now that Hynek Hermansky and Hervé Boulard have of the neural nets for front ends, and they have their hats and their traps, and I really don't understand all the details of what they have, but basically they train some kind of phone posteriors, and then they take the log phone posteriors and do PCA. And there is some really confusing things in there, because for one thing, I didn't read this in their papers, but Hynek Hermansky told me that it's very important to do PCA, not LDA. Now, that's weird, because LDA is like the canonical way that you get features out of stuff. PCA is, depending on the scaling, it's a funny kind of thing. So something funny is going on there. And now Thomas Hayne mentioned to me also that they tried to get these posteriors with mixtures of Gaussians and then project them, and it didn't work. You have to do it with neural nets. So, it's slightly confusing why this works. Yeah.
Well, then you have the same amount of context when you use the Gaussians as when you have a neural net?
He didn't mention that, but do the neural nets use much context?
Oh, yeah.
I know the hats, one of them does.
I think in that approach,
that's what they claim. They use like 200 milliseconds.
Oh, that's a lot of features. Yeah, and I wonder how essential that is. Didn't some of them take 6 months? I think at SRI they had a 6-month training schedule. That's part of the reason that I never took this up, because how could you do experiments? There are two things. I have two general objections to these techniques. Though I think it is a very good area, and I generally intend to get into it at some point. But one thing is, I have a theoretical problem, which is that they draw those graphs of one format versus the other format. And here's one val, here's the other. Theoretically, let's suppose that that's all there is in speech. That's the true dimension. So your neural nets, theoretically, when they get the posteriors, they could be first projecting to this true dimension, then doing some kind of nonlinear projection such that you get the posteriors. Now then, when you do PCA on that, you're taking this small dimension, you can think of it like a plane, and you're curling it up in some 40-dimensional space. And then you do PCA, and you're going to get something that's globally uncorrelated. But, this distribution, if you consider this line as a distribution, that's globally uncorrelated, but in a particular region, it's going to be almost infinitely correlated. Now, of course, that's not exactly what's going on, because there are really more dimensions than 2. But I think the first dimensions are clearly most important, because if you do LDA and look at the eigenvalues, almost everything is in the first 5 or 10. So I'm just theoretically, it bugs me that that's the case. And
that's why context is important, because that form you're talking about, this is just one frame in the middle of the val.
Well, that's true, but even LDA with context.
You extend that, the curve actually makes a big difference, and also the context signal form, adjacent to that.
Well, the context may make a lot of difference, but still, inherent dimension for predicting the current phone can't be as large as 40, can it? It's bound to be that most of the work the neural net does is taking some relatively low inherent dimension and just kind of non-linearly doing stuff with it. And then, how can you model that with a Gaussian? So, and of course, it's hard to set up. I'm interested in the general area of research of trying to take these posteriors and get something you can model with a Gaussian, although it seems to me a very hard problem. I guess that's why we're still using MFCCs and PLPs, because they're uncorrelated and Gaussians can model them.
Are you aware of this recent work by Bono University in Europe?
I'm not sure. What is that?
They actually took the same approach here to get posterior. Now the posterior is appended to the original capture coefficient.
Oh, yeah.
And they got a huge improvement on relatively small tasks. It's just an amazing improvement.
Really? They appended it. Did they do LDA after they appended it, or did they just appended it and used that as a feature?
Yeah, they appended. I don't believe they actually did.
Yeah.
So what was their final?
I think other people are doing that. That's SRI does. That's what SRI does.
Yeah, so like for Timmy, they actually got 80% or something.
No, 80% is after using detecting-based stuff.
Oh, I see. Okay, maybe 78.
And of course, with something like Timid, if you use a small enough model, the neural net kind of replaces your model, right? So it's hard to believe. Apparently, also, if you append them and then do LDA or then do PCA, it messes it up. You can't do that, which again is unpleasant. One of my colleagues says that he's interested right now in Bayesian networks and belief propagation and this kind of stuff. And it's an area which I'm really not that familiar with. I think there are some people here who are into that. Correct me if I'm wrong, but it seems to me that these techniques have a lot in common with trajectory models.
More general version of the trajectory model.
And I've always had the problem with trajectory models that if you're trying to model the next frame, you might as well just take the previous frame and put a very small variance around it. And of course, if you do that, you're making no attempt to model the actual value of the capture. You're just modeling the rate of change. So the actual values of the capture become irrelevant. And obviously, most of the information that you want is in the values of the capture.
It's really just a way of specifying a set of random variables that you want to keep track of. And
I guess I really shouldn't be criticizing this because it's a framework. It's not a program.
It's a framework, yeah. And you can apply it in a lot of different ways.
So, I mean, if you have other, like, in task-driven problems, if you have models that are semantic or task-driven, it's kind of a convenient way to kind of throw a bunch of different models together. But if you're not using any new sources of information, then why bother? You already have SDK, right?
Okay. Is language modeling dead? It seems to me that maybe speech recognition is maxing out, but language modeling maxed out a long time ago. I don't know if anyone's read Joshua Goodman's document, A Bit of Progress in Language Modeling, in much detail. It's a fantastic...
He's now Bill Gates' technical assistant.
Really? Is that true? So he's like directly reporting to Bill Gates?
Yeah.
Wow.
Don't worry, Bill Gates is moving down in the world.
Yeah.
And he probably won't pay attention to language modeling.
Yeah, no, he's working on spam now, isn't he? So his website. So one of his arguments is that he did some experiments and he found that you can predict the word error rate change from language modeling by looking at the entropy per word. And entropy is proportional to the log of perplexity. So suppose you reduce the perplexity from, say, 120 to 100. You think, wow, that's a really big change. But then when you take the log of those numbers and look at the relative change in the log, I don't know how this works when the log becomes negative, but let's forget about that for now. Well, if you look at the change in the log, it's very small, and really you have to get a large improvement to get a large change in word error rate. And large improvements tend to be very, very hard to get, especially once your baseline is a 5-gram Canadianized smoothed language model. And his point in his document remains true, which is that most people doing language modeling, they have toy tasks and they don't use a proper baseline. So I don't know if you guys recall. I didn't realize this lecture would be put on the internet, but
off of cable television.
we were quite excited about one point by this technique called super ARV, which SRI had, and they were getting big improvements. But it later turned out that that they had somehow used the testing data in their vocabulary selection or something. And when we actually got to the evaluation time, oh no, is this wrong?
No. I thought the years evaluation, 2003 or 2004, they actually, that was rigorous.
No. When we actually got to the real evaluation data, it didn't give us anything. I mean, it may be a valid technique. They're still using it, but it certainly.
They claimed that it didn't work because tasks become too large. I never heard that actually. But in that evaluation, they couldn't cheat on that.
Well, I think it was for some like pre-evaluation they got their big improvements. It was like with data which we had the transcripts for, and somehow the transcripts had gone into the selection of the vocabulary or something. It turned out that it really wasn't that good. I think they're getting some improvements, but they're not the exciting improvements that we were all talking about. I mean, one of who was it who mentioned this? Someone mentioned the continuous space language modeling. Holger Schwenk at Lindsay now has this continuous space language model with neural nets, which he seems to be getting quite good improvements in word error rates from. So it seems like a good thing to do, but I don't know how complicated it is.
The question is, can it really be, say, you say 5 gram, but okay, how about a 6 or 7 gram?
But I mean, I think after 5, the improvements get small.
The approach of doing things where they train a language model on the entire web or whatever it is that they're doing, at that point, the question comes up again.
Well, generalization will still be an issue even with quasi-infinite data. So it might still be better theoretically, but it's hard to say. I mean, maybe if you factor memory in, these things will give more improvement. I don't know. Okay, this is all this noise-related stuff like splice to some extent and Algonquin and this missing feature stuff. Me and one other person feel that this is a very interesting area right now, although Yasha is somewhat discouraged me by saying that you can, which is funny because you would have thought. Yeah, it's just funny because you would have thought he would be the main proponent of it, but maybe he's become jaded. So, yeah, there's a lot of work on trying to find what the noise is and trying to somehow either integrate it out or work out what the speech was or something. And there seems to have an increasing number of papers on this, and I do think it's an interesting area. You've got to, Yasha was telling me as well, and I was already thinking, you've got to be careful with these papers because they often, there's often a hidden catch, like they're not using FMLR or they have log capstral features. But I think that these problems ought to be possible to overcome them. I'm working on, I'm trying to extend the missing feature approach to be usable with normal features rather than just the log spectral ones.
Do you say this just because you think dealing with noise is a good thing, or do you think that dealing with noise will force us to create a different or more general view of how to model speech, and therefore it will be good in general even when there isn't noise?
Well, I really wasn't thinking that. I was really thinking just for noise. But there's always some level of noise because at a certain point in the spectrum, with any recording conditions, it becomes dominated by noise. Whether it's at 3 or 4 kilohertz or whatever. So I think it's always going to be an issue. Plus, most of the hard speech problems, hard conditions, relate to noise, don't they? I mean, a lot of these techniques have problems. They're not practical, or they take too much time or whatever. But maybe these problems can be solved. And it seems to me that fundamentally signals are a combination of speech and noise, and we ought to be modeling that. And especially for weird types of noise, you're going to have to come up with some kind of dynamic model. Like suppose you could have helicopter noise, or you could have music, or you could have a pure tone behind the speaker. You're never going to find one model that can model all of that.
So what kind of comment do you have on the work done at IBM for superhuman that project is something that has that goes all the direction of dynamics, they do all this.
I mean, I don't think the Superhuman project had in mind any particular technique. I think it was just a program to generally reduce the work.
Trotsky and John Hershey.
Oh, that's not Superhuman. That's the. I think I assumed Superhuman meant that I referred to the IBM Superhuman, the speech separation challenge. Oh, and they said it was Superhuman. Yeah. No, it may have been Superhuman. In fact, when I listened to the recordings, I couldn't tell, and then they totally separated them. So it was impressive. I mean, I've heard various people objecting that implementation was very highly tuned to the task, and that's true. But nevertheless, it was impressive. I mean, I'm interested in the kinds of techniques they're using. Like they're using Algonquin, and I think it's an interesting direction. But a lot of work has to be done to make it useful and combinable with standard techniques. I'm sorry?
Algonquin was already done here.
Oh yeah, I know. I'm aware that a lot of the stuff was originated here. Either adaptation method. This is a kind of a small category. It has its own slide, but this slide is about stuff related to CAT, which Mark Gales was working on, and that doesn't really work so well, but it seems to me as if it should work well. And I don't know if that merits its place here. Karthik and Peter at IBM, they got improvements over fMLR by they projected Gaussian posteriors, and I think they may have used offsets in there too. It was some kind of nonlinear projection, but they took care of the Jacobian in some way so that it could be trained using maximum likelihood. It seems to me that that's an interesting area, though I'm not sure how easy it would be to take their improvements and translate them to a more general setting. I mean, it's a little bit similar to splice and those kinds of techniques.
Weren't they doing per utterance adaptation with that, or am I thinking of something else?
I don't recall whether it was per utterance or per speaker.
It was definitely more adaptation than fMPE.
I mean, fMPE isn't really adaptation at all. It's a global thing.
It's a global thing, yes.
Yeah. I mean, it's very different from fMPE because they had few Gaussian posteriors, and it was per speaker, and it was ML. So it's just a similar functional form. I guess it's more similar to splice. I mean, maybe someone could push this area a little bit more, but I guess we'll find out. We did some experiments some time ago at IBM. I don't know if we published it. And we found that if you're adapting to a new task or new conditions, that adapting the language model makes a lot more difference than adapting the acoustic model. I guess you found that too. So it seems to me it's an important area which people haven't really looked at very carefully. But there is this technique called PLSA, Probabilistic Latent Semantic Analysis, or something like that. They have various other acronyms which mean the same thing, I think. But I think in Cambridge they've been using that in their Gale system. And it seems to me an interesting thing. And I was kind of thinking at one point of getting into that area, but in the end I felt that PLSA pretty much does all that you can do, practically speaking. So, yeah. So this is coming towards the end of the talk. This is not really current speech research, but I think it's something we should be doing. It seems to me there's a lot more information in the time domain signal than contained in just the spectrogram. And speech it may not be completely periodic, but it has some kind of structure where the vocal pulses of some kind excite some kind of filter. And it must be possible to use that information to do a better job of separating speech from non-speech sounds. But I spent quite a while looking into this area, and I found that it's a very painful area to work in because there's all kinds of nonlinear optimizations that arise. If you're trying to, say that the speech pulse is exciting some kind of autoregressive model or autoregressive moving average model, and then try to match the actual time signal, not the spectrum. The optimizations are very difficult, and it's generally hard to do. And also, I think you have the problem of local minima, which means that your results may not be so stable or continuous. But I still think someone has to work on it. Work on reducing the cost of building systems in new languages. I made these slides at IBM before I asked various people here what they thought. And I think it was Yasha who told me that you guys are working on this area too, or are interested in it. So I think that's a good thing. And various people have been telling me that applications are where it's at, but I guess that doesn't really fall under speech research, does it, in quite the same sense. Someone is interested in confidence estimation. I guess that comes under applications. And a tiny addendum. I think the whole decoding, FST-based decoding, maybe we can do better in that space and find better ways of minimizing our graphs. But of course, this is only applicable to those with those kinds of systems.
Better meaning faster decoding?
Well,
or less
like more memory
memory,
efficient, and because those things get extremely big, and it seems to me that you have to arbitrarily put these epsilons in there to stop things from going to infinity. And it seems to me like a really bad solution to the problem. Like you ought to be able to define some objective function that says we want a graph that's small and yet which doesn't have too much fan out of states with the same history. So I don't know, does anyone else have some new category which they feel wasn't represented here and which is promising and good?
A lot of areas, I think the last couple of years, people actually are looking into this non-parametric method. Since you have lots of data, thousands.
A little bit like SVM.
No,
like
it's like
DTW.
Yeah.
Oh yeah.
But once you get lots of data,
yeah.
I think maybe we'll go into this.
Yeah, I mean, it seems to me the problem is that people try to do this on word level, and then you never have that word, do you? And the word that you have might come from some weird speaker, which doesn't sound like your current speaker.
We can do this kind of like decision tree type of things to get flexible doing size. Like
yeah, I suppose that's true.
You have a lot of data, you probably can afford that word, but
yeah.
you can actually back off down to something smaller. Yeah, people are supporting that.
Apparently at Karlsruhe, they had the system where they have with global variance, and they have just individual points. It seems to me that shares a little bit with this, because each point could be an individual observation.
One of the questions that I always have some fascination about some of the work you did is that most of the things you have been doing are based on gradient descent.
Yeah, in some form.
In some form, even for the weak sense.
Yeah.
So for those kind of systems, always, local optimum actually is one of the main problems. So how do you...
that's not the way that I look at it. I'm not sure I believe it's the local optimal which is a problem. I think it's that you can optimize the objective function in a kind of non-smooth way such that you get weird things going far from their optima. And then when you decode, if there's any kind of jitter in your current parameters, that jitter will affect your decoding. So I think you have to... My experience has been that people have come up with update formulae which will very quickly maximize the objective function. But those formulae don't give good word error rate.
But they're also local optimum because...
Well, no. It's not the local optimum isn't the problem, because their objective function is a lot better than mine. So if we're talking about optimization alone, their one ought to be better. Say, I forget, Ralph Schluter, I think, had one. But if you test the word error rate, it's not as good. So I really don't think it's only a problem of maximizing the objective function. I think you have to worry about other stuff, which makes it very unpleasant, because theoretically the objective function is your definition of the thing. So you don't really want to have it mixed up in the optimization.
That's one of the SVM approach. You get rid of all this problem altogether. This is
maybe I should look into that.
From experimental viewpoint.
Well, the SVM, I think, is going... it would make this problem you're talking about even worse. If objective function, if the global minimum of your objective function isn't correlated well with a low word error rate, you don't want to be going to the global minimum. You don't want an algorithm that guarantees you get there.
Well, maybe you just have to define your objective function more carefully. Theoretically, that's what I was trying to do with iSmoothing, is to have this smoothing function. But I don't think that totally solves the problem. I think for some reason you have to do more than that.
So can you say a few words about how you came up with, this is probably the best known part of your work, is when you do this growth transformation, which sense, extending from wells, you came up with this really...
I didn't know. I guess it was...
selection of D as a function of Gaussian.
Oh, the selection of D. Well, that was even before I came up with the weak sense. It just seemed to me that it was just out of a dimensional argument, because I used to have a physics teacher who said that whenever you have a quantity, you have to work out what the dimension of that quantity is. And the thing is, in the extended Baum-Welch update, say for the mean, I think you have like the new mu equals the I forget even the notation I use, but it's like here's just a num, where a is like the mean times the count, and minus a den plus d times the old mu over blah, over something. Oh yeah, the sum of the counts. It's the count minus that count plus d. Well, it just seems to me that like this has the dimension of a count times a mean. So this really should have the dimension of a count times the mean, whereas originally it was a global d. So d should really be a count, shouldn't it? So I just said, okay, let's make d a count. Let's make d gamma times some arbitrary constant. Yeah.
That turned out to be probably the best.
Yeah, well, it seems to make more difference.
Some following up work by MPFE, etc.
Oh yeah, I think that proof was wrong, because I think I proved the opposite. And in fact, I think we now agree about where the proof was wrong, because there's a certain part of the Jensen inequality or something which relates to the fact that you have all these paths, and it's not actually equal to the log of the sum of the logs or something. It's the sum of the paths. And I think that part of the inequality he didn't take account of. I believe that you can't prove that any given finite d will work unless you know the length of the file. I think that there ought to be some constant times the length of the file. Oh no, it's also a function, I believe, of how far apart the data. Sorry?
Scott Axelrod has proof, right?
Yeah. Of what, finite?
Of finite d.
No, I think it was an existence proof. I don't think it was like... Yeah, I mean, I think Dmitry Konevsky has one too, but that's not really useful because it's obvious there's going to be a finite d, because the gradient descent problem in d is the inverse of the learning rate. So it's obvious that if it's a smooth function. And I think that was what Dmitry's proof was about, and maybe it was the same as Scott's proof. But I think it's obvious anyway. I don't think you need to prove it.
So when they prove, do they show that that number is on average in the same order of magnitude than to the number that you got?
I mean, I think you had a proof which showed that d could be 2 or something, but it was a mistake as well. It's funny. There's been a couple of.
Very wrong.
Oh well. I've never really been oriented towards proofs. I haven't bothered to. Maybe that's why I didn't get myself mixed up in these problems. Oh well. So yeah. So I think that's pretty much it. It might be a slightly short talk. But